Hello, in this video I want to talk about thermal resistances and thermal circuits. They will be very important in your chemical engineering career and also in your heat and mass course. And I assure you will have at least one question in your midterm and in your final. Well, maybe not in your final, but probably in your midterm. Um, Please study your notes, as most of these questions come from the notes. I mean, not my questions, but Professor Servio's questions usually are taken straight out from the notes. So please review all your notes and see this tools more as a support for you to better understand the concepts. The objectives of this video are for you to understand the general concept of a resistance and when to apply uh, the resistance model. Also, I want you to understand and have an idea of how to obtain an expression for, the thermal resistance, and also to be able to know how and when to illustrate thermal resistances using thermal circuits. So let's get started. Resistance is usually applied to systems where you have the transport of a quantity, and that transport of that quantity is caused by a driving potential. Um, so the resistance is basically the ratio of these two things. Basically, how much of that driving potential you need to achieve a certain transport rate. So the units for the transport rate are the amount of quantity that is transported over time, whereas the driving potential can have any units really. So resistances are usually applied to electric circuits. You might already be familiar with the driving potential for electron flow, which is the voltage. So that's the driving potential, and the transport rate is the current, or the amount of electrons that are moved over time. Um, another example that we can think of, or that I could think of, was a simple case of an ice cream truck. So imagine you're in a summer day and it's really warm outside and you really feel like getting an ice cream. And so for you to get an ice cream, you need to pay for it, right? So once you pay for it a certain price, you would basically get that ice cream, right? So imagine you're walking out and then you see the ice cream truck and you see that the price is, say, $30 for an ice cream. So it's really high. And then apart from that, you see that there is a line of, say, I don't know, 50 people. And the cost of this huge line is just that, in the ice cream truck there's a single worker and he's working as fast as he can, but he can only sell one ice cream per hour, say. So basically the resistance in this case would be the ratio of these two things. So the resistance would be expressed as the ratio of the driving potential, or the price, the amount of money that you need to pay for your ice cream, and the transport rate, or the amount of ice creams that are sold over time. So if we had, let me write that down. So because we want to compare this with another case. So we said that the driving potential equals $30 per ice cream, and then the transport rate is one ice cream per hour. Okay, let me make that bigger. Okay. Okay, so now imagine a second case where instead of having a single truck, we would have, say, 3 trucks, and you would have, say, 2 workers per truck. So now the transport rate would go up to, say, I don't know, 6 ice creams per hour. Um, so imagine the transport rate going up to 6 ice creams per hour. So transport, well, and then say also the driving potential went down to, say, I don't know, $5 per ice cream. It's easier for them to make them. Say the raw materials cost less, or something like that. So now it's cheaper, and apart from that, they're a lot more available. So the transport rate equals 6 ice creams per hour, which is still pretty low, but for our purposes, it won't really matter. So comparing these two scenarios, If we were to calculate the resistance, we would just take the ratio of these two things. So in the first case, we would get $30 hour per ice cream. That would be our first resistance. And for our second resistance, it would be a little bit lower than 1. So you can see that for our second case, the resistance decreased. So that means that the resistance for you to get an ice cream will be lower in the second case, and it will be more likely for you to get an ice cream in that case rather than in the first one. First of all, because, well, the ice cream is cheaper, and second of all, because it's a lot more available. So in the same case, we can apply this same concept to other things. So I was telling you before, in electricity, your driving potential is the voltage, and your transport rate is the current. You can also apply this to, say, if you have a horizontal fluid flow where there is no height difference, your driving potential, or what causes movement, is just the pressure force. So you can also apply the resistance concept to a pressure-driven flow, and then your driving potential would be the pressure, and then your transport rate would be the flow rate or the mass flow rate. For thermal systems, the driving potential is the temperature difference, and the transport rate is the heat rate. Basically, the quantity that you're transporting is energy, and, well, thermal energy, and the heat rate is just the amount of that thermal energy that is transported over time. So more formally, we can write it down. We write RT subscript T for thermal is just the temperature difference over the heat rate. The units of the thermal resistance are kelvins per watt, and to find expressions for the resistance, you need to find equations that relate the temperature difference with the heat rate. So I have two examples for you. The first one is the heat conduction through a system of walls in series. Okay, so imagine these are the walls here, and the walls have a cross-sectional area. Looks something like this. And they have an equal thickness. Okay, so imagine this is this wall is made out of a material 1, and this wall is made out of a material 2, and the material 2 is an insulator, and the material 1 is a conductor. Say this is a metal alloy, and say this the material 2 is a ceramic. The conductivity basically depends on different properties of the material, such as the crystal lattice or the ability to conduct electrons. Okay, so you know from Fourier's law that the heat rate is just the conductivity, the heat transfer conductivity, the thermal conductivity, the temperature gradient, and the cross-sectional area. Say in this case the heat was flowing in this direction and was coming out from here, sort of like this. So the cross-sectional area is just the area of this wall, which is the same area as the one going through the second wall. Let me just label that the conductivities are different, and the conductivity of material 1 is much higher than the conductivity of material 2. Okay, so then the expression for the thermal resistance in this case comes from relating these two equations and finding that upon rearranging we can have the delta x over k AC is just gonna be Q is just gonna be delta T over Q, sorry. Delta T over Q. So basically this is going to be your thermal resistance. Also resistances have to be positive always. So you would take the absolute value of this quantity for a resistance expression. Okay, so now we know that the resistance RT is delta X over KAC for a conduction system without any generation terms or accumulation terms. Okay, so from this equation you can see that the thermal resistance is linearly proportional to the length of the wall. So the resistance will increase as this length increases, sort of as the example that Servio says a lot in class, that imagine you're trying to run out of a building that's on fire, and imagine how easy it would be for you to just leave a building that is very short, and you're like three steps away from the entrance rather than 50 steps away from the entrance. The resistance to leave a building would be lower if the length is lower. So this would be L1, and this would be L2. Let's just say that they are equal. L2 and L1 equals L2. Okay, so that would be our L, and in the denominator you have the conductivity and the area, the cross-sectional area. So the resistance is inversely proportional to these two quantities. And the reason is that these two quantities facilitate heat transfer. The conductivity, the higher the conductivity, the easier heat will flow, and the higher the area, well, the higher amount of heat that will flow. So from these expressions, we see that the resistance makes sense. Okay, so if we were to plot the temperature profile across these two walls, we see that since the resistance for the first one, given that they have the same length and the same cross section, the resistance difference in the two resistances will only depend on the conductivity of the material. And we said that the conductivity of the first material was greater than the conductivity of the second material. So that means that the resistance for the first material is going to be lower. So R1, let's just say R1 is going to be lower, much lower, because the conductivity of material 1 is much higher. It's much lower than the resistance for material 2. So that means that to transfer the same amount of heat, in this case we neglect any heat loss from any other direction. So we are assuming that all the heat that comes in has to go out in this direction, and heat has to be constant throughout both walls. So because of that, since for the first material you have a lower resistance, you need a lower driving force. From this expression, if we rearrange as delta T equals RT times Q, if your resistance is lower, that means that your temperature difference must be lower also to transfer the same amount of heat, right? So imagine the temperature of the first material being here, and since the conductivity is higher, you don't need that much of a temperature gradient, whereas for the second material, which is an insulator, you need a much higher temperature gradient to achieve the same amount of heat transferring through. Imagine for this axis, we're just going to say that this axis is temperature. And so this is how your temperature profile will look like. And so we can see here that from the resistances, we can have a feeling of how our temperature profiles will look. Okay, so the second case is for when you have a surface exposed to a fluid. So when you have convection heat, a convection heat rate, and this would be Ts or T surface. And so the expression relating the temperature difference with the heat rate is just Newton's law of cooling, or the convection heat rate. So it's Q equals H times Ts minus T infinity, assuming heat will flow in this direction from the surface to the surrounding fluid, times the surface area. Imagine the surface area in this case to be something like this. Okay, so this is AS. And again, from comparing this equation with your resistance equation, we find that the expression for the convection resistance is just 1 over H times AS. In this case, the higher the heat transfer coefficient and the higher the surface area, the lower the resistance will be and more heat that will flow. An important concept to introduce is the concept of a contact resistance that occurs at the interface of two materials that had been mated together, say by a welding process or by gluing, and as a consequence there were some air gaps left in between, something like this. And because of these air gaps, you have a heat transfer that has been hindered, because instead of conducting directly the heat from one material to the other, the heat must go through air first. So instead of having a conduction heat transfer, you would also have radiation and convection and free convection heat transfer, which is a lot lower than conduction within any of these two materials. So contact resistances are usually expressed per unit area, and their form is the same form as for any other thermal resistance, but instead of using the heat rate, it uses the heat flux. So heat flux per unit area, and the units are Kelvin times meter squared, or area units, divided by watts. And so, say imagine you had two materials that were good conductors, and I'm going to show the temperature profile across the interface when you have a significant contact resistance. So imagine heat was flowing in this direction, and at the contact resistance at this point, you would have a drastic temperature drop, even though they are at the same distance and they have almost equal thermal conductivities. So this temperature gradient that you need is due to having a higher resistance, so you need a higher driving force to get the same amount of heat flowing across the interface. Okay, so the last thing we will go over is just how to illustrate the resistances. So to illustrate resistances, we use something called thermal circuits, where temperatures of cross-sectional areas are shown as nodes, and resistances are shown as squiggly lines connecting these nodes. So we have two cases. We have a system in series and another one in parallel. And before we start, you must know that there is one restriction, and that restriction is that thermal circuits can only be used when your heat rate is constant. So if you have any thermal generation, any material with any generation or heat sink, you won't be able to show it in the thermal circuit. That does not mean that if you have, say, only one material with generation, that you cannot use thermal circuits at all. It's just that for that material, you won't be able to show it, but for the other ones where there is no generation, you are free to do it. So let's start with the series case. In the series case, we have a constant heat flow going through both materials. So in this case, we would have three temperatures, three cross-sectional areas at which we could measure the temperature. One would be at this left edge, another one at the interface, and another one at the right edge. So we would have three nodes, 1, 2, and 3, and we can label them T1, T2, T3, and each resistance will be shown as a squiggly line. So this would be R2 and R1, one for each material, and so the total heat rate is just going to be we don't even need to know the temperature at the interface. As long as we know the temperatures and the edge, as long as we know the edge temperatures and the resistances in between, we can express the heat rate as the edge temperatures, T1 minus T3, over the total resistance. And the total resistance is just going to be the sum of each individual resistance. Okay? And this derivation you will go over in class, but it's pretty simple. You just have to know that the heat rate will be constant. So if we were to label the heat rate flowing through this first material as Q1 and the heat rate flowing through the second material as Q2, and then the total heat rate as Q total, we can say that Q1 equals Q2 equals Q total. And then the next step is to find expressions for Q1 using the temperature using T1, T2, and T3. So for the first material, you would use the temperature difference of, well, T1 minus T2 and the first resistance, R1. For the second one, you would use T2 minus T3 and the second resistance, R2. And then by knowing that they are equal, you can play with the equations and you are going to find that the total resistance is just the sum of each individual resistance. However, for systems in parallel, you no longer have a constant heat rate flowing through both materials. Here, the amount of heat flowing through each material will depend on the resistance. Heat will always try to flow through the path of the least resistance. So the main difference is that instead of having Q1 equals Q2, here the heat rate flowing through each material, when you add them up, will be equal to the total heat rate. So let me just draw it quickly. We can show the heat going through the bottom material as Q2, heat rate going through the top material as Q1, and the overall heat rate as Q total. So we said that Q1 plus Q2 equals Q total. Q2 equals Q total. Okay, I will go back to this in a second, but first let's find a way of portraying two resistances in parallel. So you would have 2 temperature nodes opposed to 3 temperature nodes because there are only 2 cross-sectional areas to the heat rate, opposed to here where you have also that interface area. Notice that here this interface area won't mean anything because our isotherms are cross-sectional surfaces to the heat rate, and in order to have just a horizontal heat rate, we cannot have any temperature gradients in the vertical direction. This is actually an assumption. This is not always the case, and when you have very different materials or very different conductivities, you may also have temperature gradients in the vertical direction, even though your main direction of heat flow is the horizontal direction. So here I said we had 2 nodes, say T1 and T2, 2 nodes, and you would have 2 resistances connecting these 2 nodes. 1 resistance for each material. This would be R1 and R2, and so the total heat rate is just the sum of each specific heat rate, or you can also express the total heat rate as the temperature difference divided by the total resistance. So Q total equals T1 minus T2 over R total. But R total in this case has a different shape because of the nature of this equation, and you will go over the derivations of this in class. So I'm just reminding you here concepts that will be useful for next problem. But yeah, thank you for watching, and I will see you on our next video where we will be going through a problem where we will be using all of these concepts. Thank you.